Okay, good morning. So today we're going to start with chapter 6, the interrupts. Before that, I want to comment on what happened last time in our demo when we wanted to operate the motor. If you remember the program we wrote, this is it. I still have it open. It is a program that configures port B as output, the most for significant bits, and inputs for the least for significant bits, and port C as output. Okay, and initiates port B. The LEDs are off, the on ones, and port C, the first 7 are off, and the 8th bit, which is RC7, is to control a DC motor on and off if a push button connected to port B0 is, I think I still have the drawing, is pushed, right? If you push port B0, there is a motor here on port actuated by the signal that we will send on RC7 to turn on the motor. And we did the circuit, and it is in the recording last time. We used a NMOS transistor in the interface. When we did the actual hardware implementation, okay, we had a problem with the push button. Let me remind you. So normally the program blinks port B and the lower 7 bits of port C infinitely. But if a button is pressed, and we checked for the button here, if the port B bit 0, we masked all the other bits, is high, then it's not pressed, so we blink. If else, then it's pressed, and we stop blinking and keep port C bits as is, and just make port C7 a 1, which will turn on the motor. Okay, this was the whole example. And to show you the program running, well, I disconnected the motor. It's in the recording of last time, okay? But you can see the concept is working. See, last time we had a problem. You see my camera, right? The board on the camera.
Yes.
Yeah, so follow the screwdriver. Port C, this is port C. All LEDs 0, 1, 2, 3, up to 7 are blinking, but RC7, which is the 8th LED, is off because this is connected to the motor, so the motor is off. The higher 4 bits of port B are also blinking. The lower 4 bits are inputs, okay? This is the push button. When we used to push the push button, these should freeze, the blinking should freeze, and port C should turn on. It didn't work. When I pressed the button last time, this is what we had. Okay, let me show you what I discovered the problem. This is what used to happen. I press the button, nothing happens. See the LED connected, it shows it, port B0 is high or low. So it's high, I press the button, it stays high. Okay, nothing happens. So I had to bring a wire connected to the pin of port B0 and then manually short it to ground, and it worked. Then I found the problem. If you see on the camera, let me enlarge the camera. How can I do that? Okay. Speakers view, but I want to see my, okay. See? Now, this is what used to happen. Nothing. Port C0 was off. I push the button, still off. Nothing happens. While what I wanted it to do is to, when I push the button, port B0 becomes low, and the thing happens. Then I found this jumper. See this jumper? And here, if you don't see it well, it says port B0. Okay, port B0, you can connect it through this jumper called J17 I'm removing the jumper now. See the jumper, a small device that shorts two pins together. There is the middle pin, which is the port C B0, and if I connect it to the higher two pins, then I'm connected port B0 to ground. When I press it, it's going to be shorted to high, to VCC. If I connect it to the lower two pins, then it will be shorted to ground. So this was our problem. This jumper was on the higher two pins. It should go down to the lower two pins. Okay. Now, if I press the button, it will be shorted to ground. See? So the LED on port B0 turned off, the blinking frozen, and port C7 went on. So the motor will turn on. When I remove my hand, everything will go back normal. Okay. So this was the problem. And there was a problem when we first started, which was this dip switch on port B0. It was in the middle. So I pushed it up to make it, if you see here, pull up or pull down. So you can pull up the button to high or pull it down to low, but the default was in the middle, floating. So when it was in the middle, it was doing weird behavior where the controller wasn't able to judge if it's high or low. Okay. So I'm going back to my camera and share the screen again, and I'll explain it more on the board here to show you what I mean. So we have two jumpers or two connections before the interrupt. So this doesn't relate to the interrupts, but it's important to understand. So this is the microcontroller, and here's the pin, port B0. Okay, and we have a button. A button looks like this, right? It has two sides here, and this is something you push down, right? If you push it down, then you're shorting these two nodes. If you release, you raise your finger, it's pushed up because, okay, and these are disconnected. So this is the concept of push button. So the push button is here. This is the push button. Last time when we started, we did not do the pull-up resistor. So it was port B0, this was connected like this, without a pull-up resistor. Okay, so, well, let me make it better. So let me draw as a pin. It was connected like this. Okay, and this was connected to VCC. Right now, you saw the jumper. There are 3 pins here, 1, 2, 3, right? This is connected to VCC, and this is connected to ground. This is the jumper I showed you. Last time, these two were shorted together, okay? When we started our program, the button was not pressed. So this was floating. This was floating, okay? So the voltage level here is not connected neither to ground nor to high, so it was floating, so unexpected things can happen. When we use a dip switch, we pulled it up through a resistor on board to VCC. And we had an option to pull it down through a resistor to ground, right? So here is another, if you want to draw it correctly, it's another jumper actually, or it's like it's a dip switch, but you can choose to slide this dip high or low, okay? So what you want to do, scenario 1, if this is pulled to high, then when you push, you need to connect this to ground, right? So scenario 1 is this, what I'm drawing around in the blue. So this is, either you do this, so your button, when it's not pressed, will read a high. If it's pressed, it will read a 0, a ground. The other scenario, I'll draw it in another color, in black. okay, is you choose a pull down resistor. Then in this case, you connect this pin to high. So your scenario will be like this. In this case, you're always, if not pressed, this is low. You read on port B0 as 0. When you press it, then you're shorting this node to high directly. So it'll read a 1. Okay? So we need to pay attention to these jumpers if we're using a board. Okay? However, if you build it on the simulator or on your breadboard, you just do the connections. You don't need to look for these jumpers. Okay, I think we cleared this thing out. Let's go back to chapter 6 and talk about interrupts. Okay. And I introduced the concept of interrupts in the past. Okay, so this is about working with interrupts. Don't forget to write your name and ID, student ID, in the chat if you didn't do yet. So we're gonna work with time, see, and we're gonna talk about interrupts, counters, and time. Okay, and timers. First, we're gonna start with interrupts. Then one type of interrupts is related to time and counters. Okay, and this is gonna be half of the chapter, and this will be another half. Okay. Okay. So we're going to talk why do we need interrupts and counters and timers? How do interrupts work? The underlying hardware structure of interrupts. How does it work? How do we deal with it? Okay. First, interrupts. When the idea behind interrupts, how did it come? We know that a microcontroller, I don't like to use the slides, by the way, but it's just to give us. Let me go get the. I want to go get the data sheet. Of the 804A. And the program memory, this one, I want to get this one. Let me just take a snapshot. Copy it and put it here. We are here, yes. So the way interrupts, well, the way we write our program, remember, we start writing our program at, this is the program memory, right? This is the program memory. We write our program, first instruction has to be here, and usually we say origin 0x00, right? So when we write our first instruction, it will be written here. And usually we say go to here, go to main, right? And we write our main program somewhere here, okay? And we do what we want to do, blink the LEDs, initialize the initialize the ports, and do everything. And we have the infinite loop here, right? So the program counter, when we first power up the controller, a power up reset happens. So the program counter goes and points to address 0, PC, program counter. Then it will fetch the instruction at address 0, which is the go-to, executes it, and go to main, which is address, for example, 20. So the program counter is at 20. We fetch first instruction at 20, then increments to 21, 22, 23, 24, until we get to the last instruction in the infinite loop that sends us back to the main loop. Okay, so which says go to 20 again, and we keep doing that. And we did this last time in our code. In our program we wrote last time, this is what we did. We had a program executing instruction after instruction. This instruction, well, this is code. This could translate to multiple instructions, right? And can we figure out what is the machine code that this translates into? Yes, we can. How? Well, if you go to the folder where we stored our program initially. Okay, I put it on my C drive. Here, when we built it, it creates an assembly program. Here's the hex. This is the executable. It doesn't matter where the hex comes from. Last time we used to do it in MPLAB when we wrote in assembly. Now we're writing C. The C file is here, but what is this .asm? If you try to open it, well, here's our machine code that the compiler converted. See, this is the main program. And this is what the compiler did generate when we did build the program, converted to assembly. So status equals status ORed by 20 hex. This will be set F status register bit number 5. Okay, and so on. So you know your machine code. Okay, you can even go deeper and know where is the machine code put if you look at the listing here. How do I do it? Dot list. Open it in MATLAB. In Notepad, sorry. See, so you get this is the assembly code that is generated by the compiler after we compile our C program. And here are the program memory locations where they're placed at. See? For reverse engineering, this is really interesting.
طب دكتور مش حكينا ما بنكتب بالبوزيشن اللي هو 4؟
Huh? Well, in C we did not say 4. In C we did not, right? Assembly we used to skip location 4. Here in C, when we wrote this program particularly, we did not say skip 4. So the compiler checked everything and it saw that we're not using any interrupt, so it did not skip. Well, when we do interrupts, we'll check it again, okay, and see if it skips or not. It's gonna skip it. Okay, so this is what happens. Code is sequential in memory. Program counter points to next instruction, next instruction, next instruction, and so on. So last time when we wrote this code, when we wanted to do something else if a button is pressed, look what we did. We put it inside an if condition, which means here, what did we see? What did we say? We said read port B, mask it with 01 hex, which means and it with 00001. So the result of the AND here is going to be true or false depending on if the bit port B0 and the button is pressed on port B0 or not. So here we're actually reading the push button. So we see it said here, read push button. If button is not pressed, do this. If it's pressed, do this. Now imagine if it's pressed, we have here a delay for 10 seconds. Imagine, I don't have this code now, but imagine if well, you know what? If it's pressed or not, if it is pressed. I want to put the delay here. See, the button is not pressed. Imagine this delay is 10 seconds. This delay is 10 seconds, okay? The program counter came here. The CPU checked if the button is not pressed. It's not pressed, so this is true. So it's gonna come execute this code. This code could take an hour to do, or half an hour, or 10 seconds. Imagine you're at this delay. You push the button, or at this delay, or at doing here something for 20 seconds, and the button is pressed. What's gonna happen? The CPU is not gonna know about it because it's not reading it, right? Until you finish here, then go back and read. So if you stay press and keep your button on the push button, keep your finger on the push button for a long time, that allows the program counter to finish all the instructions, come back, check the button, it will do what you want, but after a delay, right? It's not gonna be an immediate response. Okay, so this is called pulling. We talked about it in class when we were back on campus. Pulling. We check push button 1. Imagine our program is much larger. We have a potentiometer. We want to set the temperature. We have a push button to check if a door is open. We have another push button to check if another command. Think of a complex system like I don't know, a vehicle controller or a medical device controller or whatever. You have all these tens of buttons, potentiometers, accelerometers, all these things. Imagine if you want to read the peripherals. The push button here is a peripheral. This way, if it's pushed, do this. Then if something else is pushed, do this. Then if the temperature is equals X, do this. Then see. So if you are here and something up there happens, you're not going to know about it until the program counter goes back. And this is called pulling. Okay? So if you are doing something here, your program counter is here, and you are reading a push button here, you're not going to know about it until your code goes back and the program counter fetches this instruction again and checks for the push button. And while you're here, if another button is pressed, you're not going to know about it until your program counter goes down here after 10 seconds and reads this push button and discovers, oh, it's pushed, then do something. See, this is called pulling. And this is not practical in cases when in real-time systems. When we talk about real-time, even hard real-time systems, you need immediate response. So the idea behind interrupts came from here. Sometimes emergencies happen. So you're executing your code infinitely, but suddenly the CPU heats up or a fire is detected. You need to turn on an alarm. So there is a special hardware that detects if the temperature goes above something, then it will make the program counter force it go to this code, which could be actually code written somewhere here. See, interrupt service routine called it for fire alarm. And here go turn on the buzzer, for example. Okay. So it's a piece of code written somewhere, but I want to go to it based on something external that interrupts the normal program counter flow. Okay. This needs hardware support. Okay. This is the main original idea of the interrupts. Then this thing started expanding. This is what the book is explaining here. So sometimes, in case of emergency, you need some hardware to detect this emergency then force the program counter to go execute a different code than the one that is executing normally. Okay, then this got, okay, this is a good thing. If the door is open, then a button is pressed, I want an immediate response. Let's do something like the thing we did for the fire alarm. And then this idea of interrupts came in. Okay. I think we spent a lot of time in class, and here's another 15 minutes talking about what is an interrupt and what is the benefit of an interrupt. So the main benefit of an interrupt is you don't need to pull. You don't need to go read an instruction that checks if a port B0 is low or high. A hardware detects it for you, and if it's slow, it sends you the program counter. It forces it to go to respond to that button. Then I do, if the button is pressed, I do here what I want to do, turn on the motor, for example. When you're done, you go back and continue your normal execution in the infinite loop. Okay? So this is the meaning of interrupts. Sometimes, if you see, in our case, in our 16F84A microcontroller, when an interrupt happens, the program counter goes and points to 04, to address 04. That's why we call it interrupt vector, peripheral interrupt vector. But when a reset happens, the program counter goes to address 0. Sometimes they combine them together and call them resets and interrupts. Well, a reset is an interrupt. It forces program counter to go to 0, and interrupt source also forces the program counter to go to address 4. What do we mean make the program counter go to address 4? Well, the program counter is a register anyways, right? Program counter is a register. You just make hardware write the address 04 in it, 000, 0100, right? Well, 13-bit. Mashi? So hardware writes zeros and ones in the program counter, then the program counter starts pointing to that location and does what's in here. So here you say when an interrupt happens, you say here go to, instead of go to main, go to interrupt service routine, and you write your interrupt service routine somewhere in the memory below. Tamam. The 16F84A microcontroller we're studying, well, that we started with, but we're using the 77A. We're going to expand to it later, and it will have more interrupts. For the 16F84A controller, we have 4 sources. Oops, what happened? We have 1, 2, 3, 4 sources of interrupts. These are the only 4 causes that can cause the program counter to stop its normal flow and go to address 04 to the interrupt vector. Okay? These are the 4 sources, and they have underneath hardware support to make the program counter go to that interrupt service routine. We're going to learn about these 4 interrupts. We're going to spend some time in this chapter, and we're going to do a lot of examples. Okay. In an example, we learn multiple things. You learn about the interrupt and other stuff on the way. So but to summarize, the first source of interrupt is called the external interrupt. And this is the only external interrupt input external to the microcontroller 16F84A microcontroller. Well, the 16F877A microcontroller has more interrupts. We're going to study, we're going to have a look at them and use them when we get there. There is a special chapter on that. But it's going to be like something very similar. So if we understand these, the other interrupts will be easy. This external interrupt is tied or shared with port B bit 0. You know the pin we used last time in our microcontroller where we had the push button? This push button, we read it in a way, normal way. We checked read port B bit 0. If it's high, turn on, do this, else do this. But this is supported with an interrupt. capability, which means we can do some configuration, make the hardware detect if a rising edge or a falling edge, we configure that, is detected on this pin, bit 0 of port B. And in this case, you don't treat it anymore as a parallel port. It's an interrupt pin. Okay? Then it will force the program counter to go to address 04. Okay? So we're going to look deeper here. We're going to write an example. I think we're going to start with this example today. I'm not sure if we finish it, but we'll start with it today. The other source of interrupt, the second source of interrupt, is a timer overflow. If you remember when in the first chapter, when we studied the architecture of the microcontroller, we saw that there is a timer called timer 0. For short, it is written, the register, it is tied to a register called TMR0, timer 0. This timer is an 8-bit timer, counter actually, 8-bit counter, 8-bit. And it increments on a clock. We configure the speed of this clock. An 8-bit counter counts from 0 to 255, right? Which is 0 to 0xFF, right? Because 8-bit. After 255, if a clock is detected, the counter overflows and goes back to 0. This overflow, we can make it trigger an interrupt. And in this case, we mean trigger an interrupt means that a hardware will detect this overflow. When it happens, it will send the program counter to do something. Imagine how useful this could be in delays, for example. So what we do in delays today, we write, when we did the blinking of the LEDs, the code running on our microcontroller, we used time wasting loops delays, right? We go turn on port B and say do no operation, no operation, no operation 500,000 times. The CPU is busy doing no operation. It is busy, but doing no operation. Then after when that's done, we turn off the port B. Imagine if we use this, we can go turn on the LEDs on port B and enable this interrupt to cause an interrupt when the time elapses, the 500 milliseconds or the whatever, we can configure the time. We're going to look into this very deep. Then you go back and turn off the LEDs, during which between the two times before this interrupt happens, you can go be doing other homekeeping stuff, checking other sensors, doing other operation calculations, etc. Very useful, very useful. So we're going to study this and this will be the second half of the chapter. Okay. Another source of interrupts is port B interrupt on change. And if you go back to chapter 3, when we studied the parallel ports, you can see the external, we had port B interfaces, the tri-state buffers and the flip-flops. If you remember, go back to the recording and the slides, you can see them. This has something, port B0 had something different, and it had an external interrupt piece in that architecture. And the most four significant bits of port B also were different. There was, remember, there was an XOR and two flip-flops. One is captures the port B pin value, but when you see, after you say read port B, this is locked, and another one starts capturing the value afterwards. And if these become different at any certain point of time, the XOR will say, right, any two inputs to an XOR will cause a 1 on the XOR, right? So and we get the 1, and this will trigger an interrupt. Go back to chapter 3 to check it. So this interrupt says, whenever you read port B, after you read them, you read port B, like you say, if port B equals something, you read port B, you accessed port B in your program, if it's input. After that, after you read it, what you read is stored somewhere. Then, if anything is changed after you read it, in the first highest four bits, which means port B, 4, 5, 6, and 7, 4 to 7, any one of these changes, this would cause an interrupt. Okay? This means that we can tie another 4 pins to external hardware sources, to a trigger that is pushed when a door is opened, when a window is happening, a switch, a contact switch, whatever. Okay? But you will not be able to, the interrupt will not tell you that pin 4 has changed or 7 has changed. In that case, you will need to check it manually, by reading the port B. Okay? So any change in port B, they call it port B interrupt, but it's not whole port B. It's only the most 4 significant bits. This will cause an interrupt. Cause an interrupt means send program counter to 04, to address 04 in program memory, and do something else than what you were doing before. The last source of interrupt is E2PROM write. When we explained how the E2PROM is executed, when you write any data byte to the E2PROM, it's not writing to the E2PROM is not as fast as writing to the RAM. So it would take time to complete writing. So when you write, you need to keep waiting for a flag to raise that hardware is done writing the E2PROM. You can go write the other byte or whatever. If you don't want to wait, just like getting stuck in a hardware delay, in a loop delay, you can just enable this interrupt source. And when the writing to the E2PROM is complete, you'll get an interrupt. And then in interrupt service routine, you go handle what you want to do next. Okay. So these are the 4 sources of interrupts. We're gonna go into them deeper. We're gonna do a lot of examples here. Any questions so far? All good? Okay. So let's look at okay, what's going on? The images are not here. Let me try to open them again. Something weird happened. Don't save. Okay. So the interrupt structure, looks like this. Well, before the structure, interrupts are usually 2 types. Maskable interrupts. Okay, how can I write? Oh, yeah. Maskable interrupts. Type 1. Type 2, non-maskable. Non-maskable interrupts. What does this mean? Maskable interrupts means that you, in your program, have the control. You can do the configurations to mask them, which means disable them. So you don't want to know. You don't want somebody to interrupt you when you're doing something important. Okay, when you're inside in the middle of something important, you don't want the external interrupt on port B0 that's tied to somebody ringing a doorbell or opening a door or whatever to interrupt you, because what you're doing is more important than the interrupt cause is. So you can disable an interrupt at some pieces of your code. Okay, that's called maskable interrupts. But there are some interrupts that are not maskable. Okay, you cannot mask them. Non-maskable interrupts. You cannot mask them. So a maskable interrupt, when it happens, if it is enabled, it will cause the program counter. Interrupt the CPU. What does interrupt the CPU means? It means make program counter become 0x04. Okay, this is the meaning, which means the program counter stop doing whatever it's doing, go execute a special code I wrote that starts at address 04. Okay, but the non-maskable interrupts, and these ones, the maskable interrupts, you can disable them, which means they can, you have the control to disable them and prohibit them from making the program counter go into this address. But for non-maskable interrupts, you don't have control over them. When they happen, they happen. A simple example to give you an idea, a reset, the master clear is here in the literature of the PIC, they don't call it an interrupt, but it is really an interrupt. The master clear, when you push the master clear button, you cause a reset, the program counter goes to the address 0000, and you don't have any way inside your code to disable this. Okay, so this is a non-maskable. We don't have any other non-maskable. We don't have any non-maskables in our 16F84A microcontroller, but other processors do have. Okay.
دكتور.
So, yes.
دكتور طيب بس الماسكبل بقدر يعني الفكرة إنه الماسكبل بقدر أسوي له كنترول والنون ماسكبل لا.
Yes, الماسكبل you can mask them يعني you can disable them.
من الجلوبال انتربت انيبل ممكن صح؟
هسه عم نجيهم يعني there are multiple levels of enabling في global وفي local. Okay. بس المهم في as a concept you can disable them or enable them the maskable.
بس النون ماسكبل هي خلاص إنه إشي
no control.
إشي ما بتقدر تسوي له كنترول أنت أبدا.
100%. Yes. 100%. Okay. So two types. So see the non-maskable, I'm going to start with the non-maskable. They go directly interrupt the CPU. Interrupt the CPU meaning changing the value of the program counter. You don't have anything in between. For maskable interrupts, you have enables. You can enable or disable them. Okay? There is a global interrupt enable bit, and this is a bit in a register. We're going to see it. If you make it a 0, then whatever comes from here, the output is always 0. You're not gonna interrupt the CPU. Okay? Whatever happens here, then you masked. أنا قاعد بغطي بإيدي قال فكر شايفيني. When you mask, then يعني all this thing is gonna disappear. Whatever is here, if you write a 0 here to this bit, you globally disabled all interrupts. All interrupts. What are the all interrupts? هذا هم. External, overflow, كلهم. Any one of these, if it happens, is going to disable. It's not going to be detected. The program counter is not going to respond to any of all the interrupts. طيب. This is the global interrupt enable, we call it. Okay, so this is for all interrupts. Now for each individual interrupt, yani for each of these four, and in other controllers we have more than 4, we have this configuration. Okay, yani assume this is for port B0 for external interrupt. What do you call it here? External interrupt. Okay, this is for the external interrupt. Well, we have another one like this. What's inside for the timer 0 interrupt. Okay, and it's tied to here. And we have another one for the E² prom interrupt. Okay, and it's tied to here. For all 4, these are 4. 1, 2, 3, 4. For the 4, any one of them, and this is an OR, right? So any one of them, any one of these 4 happens, it will trigger an interrupt here, any one of them, or if the global interrupt enable is enabled, then the signal is going to propagate and go interrupt the CPU and change the program counter. Okay. تمام. So because there is no space, يعني high is not drawn 4 times for each, but we have it replicated for each of the interrupts. طيب. Now what's in here? Interrupt X. Let's say interrupt X is the external interrupt. When an external interrupt is detected, what does this mean? Detected, there is a special hardware that detects if there is a rising edge or a falling edge. Is detected, then this is a 1. And there is no reset to the CPU. This is an SR latch or flip-flop. SR set reset is you need to remember. Okay, I cannot scroll. 0, 0 means no change, right? Okay, I don't have 0, 0, no change. Set, reset, and Q. 0, 1, I no change. 0, 1 will cause a reset. Will make Q 0. Q will become a 0 if it's 0, 1. 1, 0 is a set, and 1, 1 is not allowed, right? So we look at these cases. So when an interrupt is detected, this becomes a 1, assuming there is no reset. This is connected to the CPU reset, is a 0. So this is a set. So our Q will raise to high. And this is tied to a flag. We call it interrupt flag. It's a bit in some register we're going to see later. Becomes a 1. But this flag alone is not going to interrupt the CPU. It's not going to change the value of the program counter, okay? Unless there is an enable, we call it a local enable for this interrupt X. If it is 1, then 1 and 1, if it's not enabled, then this is 0. Even if you get an interrupt, something asked for an interrupt, it's not going to propagate because this is going to be 0. But if you enable the interrupt locally, the signal will propagate to here. Then if this is all interrupts are globally enabled, then it's going to interrupt the CPU. If it's not, okay, if it's disabled, it's not going to interrupt the CPU. Now, why is this SR register important? So you interrupted. So a rising edge is detected on the external interrupt. Then somebody opened the door, then it closed the door. So this is not 1 anymore. It went back to 0. Okay, went back to 0. 0, 0 is no change. So the 1 will stay there. Okay, this 1 and this flag will stay 1, and the 1 will stay there. Okay. This is very important because sometimes an interrupt could come in 5 seconds, and you are doing something, serving another interrupt, doing something. Okay, you need to know if an interrupt happened while you're busy doing something more important. So this flag will stay raised. Okay, and you in your interrupt service routine, when you service the interrupt and you're done, you blinked, you did the buzzer or whatever, you go clear it. Okay, you clear it. You write a 1 here. Okay, and you clear the flag. This will become a 0. Just like when you're in an airplane, for example, you want any service from the helper. You push the button that for the waiter, I want something, right? Turns on, a light turns on. The waiter will see it and will come and ask you what you want, and he or she will serve you. But the first thing she would do or he will do is turn off the light or lower the flag. So it doesn't serve you, and somebody else sees the light or the flag raised again and keep doing that. A lot of people write programs and forget to clear the flag, the interrupt flag in the interrupt service routine. So their program hangs, بجمد, بيعلق. بروح بكتب برنامج in the interrupt service routine بنسى يعمل clear للانتربت بعد ما يخلص, فبس يطلع السي بي this will يعني اذا ظلت 1 راح ترد تعمل البروجرام كاونتر ترجعه على نفس المكان, فبضل معلق بالانتربت سيرفيس روتين لانه he did not clear the flag. Okay, so we'll continue next time. Thank you. Time is over. I took a few more minutes from you. Okay, thank you very much. If you have questions, you can stay, but I'm going to stop the recording for the sake of the class. We'll continue next time. Next time, we go deeper and we write some code. Okay.
دكتور بس بالنسبة للريسيرش بدك إياه بتمبلت معين ولا عادي؟
Okay, let me just stop the recording. Thank you very much.